Okay, so we're live now. Okay. Hello, everyone. I'm going to present in English, right? Yeah, okay. I'm going to present, I'm Leticia. I'm going to present the type 2 Seesaw mechanism. Just a small review. Okay, so. Huh? That's a problem. I don't know what it is.
Click quickly.
No, it's already.
Yeah.
Oh, okay. But it's like this, and I don't know why. Okay.
I think if you faz uma vez, tu
Ok.
fechar, tu tirar
Fecho.
a tela cheia do teu computador e abrir de novo, vai ficar normal.
Então, eu tentei fazer isso, ele ficou bom, só que aí depois ele voltou a ficar ruim. Não sei por quê. Vamos esperar. É isso. Okay, so first, some weeks ago, Ricardo explained to us the type 1 Seesaw mechanism. It's not necessary to know the type 1 Seesaw mechanism, but I will assume that the things that he presented, I don't need to present anymore, like the measure and mass terms and whatever. So this is like a brief review of what he presented. So in the standard model, we don't account for massive neutrinos, but we know that neutrinos are massive because of the neutrino oscillation. So the most simple way to obligate that neutrinos are massive in the standard model is to propose a sterile right-handed neutrino, and that would generate a Majorana mass term. And you have two cases. If you consider that this term is zero, you have lepton flavor conservation, and you have a massive neutrino, but you have to do a fine-tuning, stream fine-tuning on the coupling. So normally we consider a Majorana mass term non-zero, which causes lepton flavor violation, and this we call this Seesaw type 1 because we have a relation of the more you improve the mass of this right-handed neutrino, the less massive the mass of the real neutrino will be. So the Seesaw mechanisms in general are all basically the same concept. You have a large scale to explain a small scale in the mass of this little neutrino. In the case of the Seesaw type 1, this is what I took from Ricardo's slides. You have this relation, right? This M nu is the mass of the neutrino, Mr is the mass of the right-handed, MD you put to one Jeff, and there you have it. Okay, so the differences between the two types of Seesaw. In the type 1 Seesaw, you have a right-handed singlet, that is the right-handed neutrino. So this H, what's the name of it? Brackets, is the scalar field, the VEF, I think. This means that in the between interactions of this new left-handed, there will be a sterile neutrino that will interact, and later you can have another flavor of left-handed neutrino. In the type 2 Seesaw, you have a scalar triplet, so you doesn't introduce anymore. What is this? You don't introduce anymore a singlet, but a scalar triplet that will be added just like the Higgs. And here you have, let me put in the board. This is because I didn't find an image. Pretend that this is special. Here you have the H, the vowel of the here the neutrinos, left-handed. And here you have a coupling, yes, it's the UCAL. Here you have a UCAL coupling that will be of this mass, this lambda. This mass delta, yes. This delta will be the triplet. So this will depend on the mass of the triplet. And this is their interaction, UCAL interaction between this scalar and the left-handed neutrinos. And this will be a coupling that also defines the electron flavor violation. Why exactly this defines electron flavor violation? I didn't quite understand. So if you know, please tell me.
It's not predicted by the standard model, but it's not forbidden either. The electron flavor violation.
Yeah, no, because this mu is related to the electron flavor violation. This is what dictates if it has electron flavor violation or not.
So it's a model similar to the one I presented. And
Yeah.
you can have flavor violation.
Yeah.
But you cannot have that in the standard.
Yeah. So that's basically
You have the Lagrangian?
I have. I will show.
Because I think there is some,
Yeah, this mu is I will show in the Lagrangian. It's related to
explicit,
triple interactions.
these scalar equivalents have the electron number.
So here you have to introduce the type to Seesaw, you put a scalar triplet plus the Higgs doublet. So it'll be like a Higgs kind of triplet. And you can do a similar representation to what you do in the Higgs. Here you have the triplet, the delta triplet, and here is the S2 representation in terms of the polymetrics. That's what we were discussing, but I didn't have this unfortunately. So you have three fields: the neutral one, the singly charged, and the doubly charged. And to interact with the SU2 group, with the standard model, it has to be represented by a 2x2 matrix. So, as I told, we have a similar.
Doubly charged. What? Sorry, is it charged? Is it electric charge?
Yes. So we have a similar assumptions between this triplet and the Higgs doublet in the terms of the VEV. Okay. Is it better if I took out of full screen to not be, because this is pissing me off. Maybe. Well, this is bad either, right?
You download it.
Okay, I will end it because if I download, maybe it will. É porque eu tô apertando, só que ele começa a piscar atrás do que estava acontecendo. Deixa eu ver se é rápido baixar.
Eu acho que o electron flavor violation é assim, vai o CKM, né? Quando você
Sim.
inclui as massas, os partes se misturam.
Sim.
Então agora você vai fazer uma coisa parecida.
Let me see if it... Okay. Is 11?
Acho que vai ter uma apresentação.
Qual é a apresentação?
Logo que eu apertou,
Ah, tá.
aqui na apresentação.
Please don't vote. Okay.
Mesma coisa.
Okay.
E agora não vai.
Cool.
Mas você não
Fine.
vai.
Yeah, okay. I
Só
will put
fechar
this.
a aba da X. Round.
Ok.
Se no F11 não fica, não.
Não, eu dei F11 antes e ele... Agora, se ele conseguir 10, pronto. Where was I? Oh, I wasn't here. Okay, so pass the slide. As we are adding like Higgs, the scalar Lagrangian will be modified in the standard model, as well as the Yukawa Lagrangian. So the Yukawa Lagrangian will have this. You see my cursor? Yeah. You have this type of interaction, Majorana, and the scalar potential. In the scalar potential, we'll have this heat scalar potential, as we know, the triplet scalar potential, and the interaction potential, the mixture between the both. Okay, so if you open the scalar potential, you have this. This first two is the Higgs. Then we have a mass term to the delta. And here you have this. Oh, sorry. Stop it. Okay. Here you have this mu. This mu will be associated with every three interaction components. And that's what I was talking about. This will dictate the lepton flavor violation. So if we consider mu equals 0, you have no lepton flavor violation, but it also implies that you have two extra scalar neutrino flavors that will interact with the Z boson. So the Z boson would have an invisible decay in these two neutrinos. So this is ruled out by many collider experiments and etc. So this can't even be considered. And normally we consider the one that includes lepton flavor violation. That is the mu different from 0. Okay, so
Because the bounds on lepton flavor violation are very strict also.
yeah, you have to have a mu, very small mu, I think.
Have very precise mu decay.
Yes, and this is in fact constrained as well. Like, and in the end, there is a graph that I will show with the constraints. Okay, so if we consider the minimum of the potential, we find the two masses, the mass for the Higgs and the mass for the delta, the triplet. This case, we know that the mass of the Higgs is just this first part, and we know quite precisely. So the other two terms has to be small. So what we consider is this, the VEF of the delta, that is this V delta, is really small, smaller than the VEF, much smaller than the VEF. And this lambda 4 and lambda 5 are similar. So here you have the Higgs VEF and the triplet VEF. Okay, so with this and more mathematics, algebra, we will end up with this relation of the VEF of the delta and the mass, and assuming that the Majorana neutrino mass matrix is described by this relation, we can substitute the VEF, and we have the Seesaw relation that is, as you can see, similar to the type 1. In the case of, you have a big mass for the new scalar, and you have that justifies the smaller masses for the neutrinos, the actual neutrinos. But you have two extra parameters In this case, that is this mu, that is that coupling, and this Yukawa coupling with delta. So finding the mass eigenvalues, like you consider the minimum of the potential, and you continue the equations. We'll end up with 7 physical bosons and 3 Goldstones. These 7 are the doubly Higgs, this doubly charged H, that is from the triplet, the positive and negative, a single charge, positive and negative, a neutral one, the Higgs, of course, that is also neutral, a pseudoscalar, A, and I think that's it. And the other ones are Goldstones. So this is the relations that we get for the singly charged and the doubly charged, and we can put constraints in this too, based on collider experiments, or the whole parameter that has to be one that will also change when we consider the type 2 Seesaw. So here, I don't know if you can see. You can't. I will put a zoom in it so you can see the names. Here's a graph that constrains the parameter space of the mass of the doubly charged H, the new scalar, and this VT is the V delta, so it's the VEF. As you can see, you have an upper wall that is from the whole parameter, because you can't have this to be much large, because this whole still has to be 1, and you don't have much uncertainty on this value.
Is this perturbative, or is this because of the VEF you show the comparison with the standard model VEF?
No, this is because of comparison with the standard model of VEF.
That's stronger than perturbative.
I'm not sure.
Yeah, I don't think.
I can show. I have here the some papers that talk more about this parameter space. I can show you or send you. So here you have constraints as well from lab experiment, from LHC, 7TeV, 8TeV, and 13TeV. Here are the constraints on the muon to electron gamma process in terms of lepton flavor violation. So this two, this is the muon analogous magnetic moment. I think it's this purple line, this green line constraints regarding the lepton flavor violation. So you can't have a VEF that is too small. In this purple part, if I'm honest, I forgot. Actually, I'm sorry. But basically, this is the parameter space that's allowed for this VEF. And I think it's not more appealing, but the type 2 Seesaw has the advantage of not going to such high values on the energy that you require. And it's basically the end. Oh, yeah. Thank you.
I think I got how they have lepton flavor violation because of the terms of the Yukawa interaction between the two triplets and the leptons in the standard model. It comes with a Majorana term, so it's necessary somehow that the triplet will have some kind of how can I say, lepton number
Yes, it
And
has.
then when it goes to the potential, only tripole terms
Mhm.
like this, because the others are always particle anti-particle.
Oh,
In that
okay.
case, it's
That's why it's
just-
free.
That's why it's the potential.
Right.
Because you have just like
Now you say it more simple than I thought.
it's just like this,
Mm-hmm.
and then you have something like this.
Yes.
And all the other terms that involves this guy is something like this. So any other can give
Mm-hmm.
because they cancel,
Yeah,
but this one
I got it.
doesn't.
Exactly. So, any more?
Question?
Yeah, questions or
Everything is what I
comments?
said. So let me. Okay, so
And this is the most that I could find about the S2 representation. You represent this delta in terms of the Pauli matrices.
multiply by the.
Yeah.
Yes, that's
And
exactly.
is it?
First case.
It's good.
And forget it from Is there any other parameter space region that's interesting to see? Like, because you show the mass
Nice.
of the doubly charged and the value, right? But did you find any other paper they talking about other parameter spaces like this?
Yeah, actually, I found, but I didn't read further. But let me see if any one of these here. This is not. Let me see here.
I think it's
And this is the VEF, and
the difference of the mass.
this is the mass. Are you seeing? I can put a zoom.
What other parameters are
Hmm.
there? But doesn't it give verbs and
It's the value of the triplet.
Yeah, this is the
and
VEF.
difference of the masses, so the low
Hmm.
masses. I
well,
think
then
it's
it's probably the neutrino mass.
Let me see.
perhaps.
Because we can measure the difference between the
Yes, exactly.
Yeah. Yeah, neutrino mass.
Neutrinos,
And spectrum.
neutrinos,
Yeah, M1.
that,
So experiments like the neon decays and the LHC, we would actually measure the properties of the triplet,
Yes.
not the neutrinos directly.
Yeah.
And then the neutrino experiment, you would like to measure the difference of the masses of
No,
the neutrinos.
not only because this is about the difference of the mass, but the one I showed, we were constraining the mass of this doubly charged.
Yeah.
Not the difference.
No, I think this one should be the difference of the neutrino mass.
Yes, this one is the difference between neutron masses. Okay,
Because
I understand.
you're focusing experiments that are measuring this observation.
Okay, so you're telling that don't constrain the real neutrino mass, right? Like the
Yeah, I mean, you do the
The
whole
Mu?
seesaw to obtain the neutrino masses.
Yes.
The observable we do for the experiment is the
Yeah.
difference between the neutrino masses. Now,
Yeah.
if you go to the LHC, we would
Mhm.
do searches for doubly charged scalars,
yes.
not neutrinos. So it's more
Yes.
interesting to write this parameter space in terms of the masses.
Mhm. I think it's just this one. Let me see here. maybe this one.
This is a paper about how to make biogenesis from that.
This relates as well the difference of the masses of the neutrinos.
I think it's the message that you
No, here.
Yeah, it's the message that you
Not in
they scale.
And the mu. Yeah, so I found many different graphs, but I just included that one because I thought it was more illustrative.
Thank you.
Thank you.
but that one was clearly not representative.
I can send you anyone if you.
The live.
The live, right? Okay. I will stop presenting.